So, yeah, I work at 4HP, and I get to spend all my time hacking on upstream stuff, in particular the OpenStack developer infrastructure. And what we do is we build the tools that are needed to develop OpenStack in the open upstream. And we do that for over 1,000 developers at this point, and they're pushing hundreds of commits every day. And so we're building things like code review systems, CI systems, collaboration tools. We host an Etherpad, a wiki, and so on. And the idea is that if we can build these tools upstream, then there's no excuse for people not to develop and work upstream. And we think we can provide world-class services there and foster and make the development of OpenStack go quicker. And so today, I'm going to talk a little bit about how we've scaled that to over 1,000 developers who can push hundreds of commits every day, because we found that it's often not very trivial. And in particular, some of the challenges that we've run into and how we've gone about solving them. So I think everyone here is probably pretty familiar with what OpenStack is and what it does. But there's a lot more to it than just building private and public clouds using open source software, especially from a development perspective. There's a lot of projects at this point that make up OpenStack. We've got the server and client libraries, and they all do very different things. We've got compute that talks to hypervisors. We've got Heat, which does orchestration. We've got object and image services and block storage. There's Ceilometer does measurement. Horizon is a dashboard. They all have very distinct needs. They do very distinct things. So testing them, hosting their software is often difficult from the perspective of trying to support everything all at once, especially when there's only a handful of us doing it. And we're constantly adding new ones. And in fact, my list is already out of date because Savannah was recently incubated as well. But we've also got projects in the pipeline to become integrated as part of these projects that are released on a 6-month basis. And so we need to be able to scale and handle new projects coming in with new needs that are different, right? So the Trove is doing databases, Ironic is booting bare metal Nova hosts, Marconi is doing message queuing, and Savannah is doing MapReduce with Hadoop, I believe. So they're very distinct testing needs that they all need. We also have horizontal efforts that OpenStack has dubbed programs. Things like documentation. The documentation team is doing documentation for the various projects, Nova, Cinderglance, et cetera. The infrastructure itself is a program. We're self-hosted. We want to run all of our stuff in the open as if it were one of these programs. And it is. There's Oslo, which is common libraries that are used across all of the projects. Quality assurance, so things like Tempest and the actual tests themselves are a program because they're testing a wide variety of the projects, and they're doing integration testing across all of them. Release management, translations and internationalization, and vulnerability management. So we've got a wide variety of things that we're trying to support upstream and in the open. And a lot of these, especially from a programs front, they're not typical software development problems, right? Documentation, they're not doing software development, they're writing docs, and we need to be able to support their needs as well. The release management for OpenStack is on a 6-month time-based release cycle. It's similar to Ubuntu and Fedora's release cycles. And we do a design summit at the beginning of each cycle. So we basically end up having a week where we plan everything, and we've then got 6 months to implement what we've planned. So we don't get a lot of lead time on the new requirements that are coming in from the projects and the programs. And so that means that, we have to be able to iterate quickly and get new things in the pipeline. We also develop on a continuously open trunk. So rather than having special dev branches or stable branches and complicated branch setups in Git, we just develop straight on master. And that means we need to keep master working. We can't break it, which is a big part of what we do. And I'll talk about this later, but we run what we call a project gate, which is where we don't let any broken code into master. That's the theory anyways. We've got intra-cycle milestone releases. So within a 6-month cycle, we have these mini cycles that create pressure on us as well, especially around feature freeze. So about 2/3 of the way through a release cycle, we get this huge stampede of people trying to push their code in before feature freeze happens. Otherwise, they have to wait until the next release, which is not what anyone wants. And then there's post-release stable branches, and we support 2 of those. So currently, we support stable Folsom and stable Grizzly branch. So we have to be able to run tests and provide code review and things like that for these stable branches, as well as a working master. We've also got a lot of contributors. At last count, we had, it was like 1,064, don't quote me on that number, but it's in that range of active technical contributors, and they come from all over the place. There's unaffiliated individuals, commercial entities, nonprofits, government agencies, and the number of contributions, the quality, and their goals change. You know, some folks are interested in fixing the bug that's been bothering them in their deployment. Other folks want to support their hardware, and so on. And we need to be able to support the wide range of needs there. And we've done that with consistent tooling. We want to minimize meta development. We've got a lot of projects, there's programs. We need to be able to solve these meta development problems once. Process, we should solve that once, and do it in a way that's applicable to everyone. And then that way we're not wasting developers' time solving these problems over and over and over again. A big benefit of this is it lowers onboarding time, particularly across projects. So if you've contributed to any OpenStack project, it's really easy to then contribute to another. So if you've pushed code to Nova, you should be able to just push to Swift and the process doesn't change. It's really easy to do, and that's a good thing. It also allows us to consolidate our tool development. We end up building quite a few tools ourselves because there's not really any alternatives out there. And not needing to build equivalents for each project is a good thing. We can consolidate them together, Nova, Swift, CinderGlance. Everyone can make use of those same tools, which is good for us because we can spend more time doing other things or building new tools. And then project-specific weird build crud. With Havana, we're seeing the first release of Python build reasonableness, also known as PBR. You can blame Monty for the name choice. But the idea there is that we should be able to release packages for all of our projects consistently. We don't need to maintain each of these package build environments independently. Because when you do, you end up with lots of weird build crud. Like versioning doesn't come out right for this project, and it doesn't come out right in this other way in another project, and so on. And we try to be consistent to reduce that, that build crud is what we're calling it. But we end up with this giant list of things that we run and support or build. There's code review and VCS. So Gerrit is our code review system. We do a lot of Git-related things. We've run a test and build automation system using Jenkins, Jenkins Job Builder, and Zuul. We run our own repository mirrors because upstream repository mirrors tend to fail often enough that we notice when we run our tests. And then there's other things to do collaboration like wikis and etherpads, just documentation, publication, and so on. So this is part of the solution, but it's also part of the problem, right? There's only a few people doing this stuff. Running a bunch of tools like this is, you know, not ideal. So the development environment for OpenStack is Python. OpenStack supports Python 2.6 and 2.7 today. Currently, support for Py3K and PyPy are in the works. I think some of the clients maybe, Joe would probably know better. I think a few things no, he says no. So I don't think we're quite there yet, but we do have the ability to run tests under those platforms so that we can start getting those features out. We enforce PEP 8 standards so that we don't argue, or at least there's less arguing over style and formatting and things because we're just consistent and say everyone needs to follow PEP 8. And as much as we can, we consolidate code into Oslo, which is the common library for OpenStack. And that way Nova and Ceilometer and so on aren't reinventing the wheel internally. We can do it once and distribute that within the other projects. And we make heavy use of virtual env, pip, and talks. As a developer, it's really easy to run the tests locally because all you have to do is type talks in a command terminal and it'll run all the tests for you. And that's what we want. That's the goal, right? It should be easy for everyone. And Tux, Virtual, and pip make that easy. We've also distributed environment onto IRC. This is common with open source projects. But it's handy. We've got 24/7 coverage for the most part for most projects because everyone's on IRC, and depending on your time zone, there's someone there to help out. Devstack is a big part of the development environment because it turns out deploying a cloud is not easy. And Devstack makes that easier for developers to do so locally. You know, granted, they're simple clouds; they don't do much, but it allows people to interact with the actual, you know, bits and pieces that they're talking to. And the nice thing that Devstack will do is you can grab your Devstack configs and reproduce an environment that someone else has built to try and, you know, correlate bugs between, you know, certain instances. We also use it in the test environment. So Devstack is used to build OpenStack when we run OpenStack tests. So running tests is a big part of what we do. Every time you push code to Gerrit, our code review tool, we run tests on that change. And that happens for every newly submitted change. So we run a lot of tests. But even more so, we gate code merges on tests. And what that means is that before any code merges into master, which we keep open and what we develop against, we test you again as you would be merged onto master. So we're testing the end result of being merged rather than the code itself that was submitted. Because that's the end result, right? We want to make sure that master itself doesn't break. So we need to test what master would look like if you did merge. And we call that project gating. It ensures code quality. And a big thing it does is it protects developers. You don't have to think about where to grab working code. You can grab master, start hacking on that, and you're good to go. And it protects the tree. Bad code doesn't land, in theory. Sometimes things sneak through, but by and large, it protects us from having massive breaking things that, you know, confuse everyone and require fixes to go out quickly and a lot of communication. We can protect ourselves from a lot of stuff simply by preventing merges that would cause breaking. And it's egalitarian. The process is the same for everyone. This is really good for new contributors. You don't have to find out who to talk to or, you know, the special merge process for this particular piece of code and so on. You push it to Gerrit. It's on your code review. The process is the same for everyone. There's no secret like buttons or people with merge capabilities and so on. But it does mean we run a lot of jobs. Up here for milestone 3, which was, what was that date? A couple weeks before milestone 3, when we did feature proposal freeze around August 27th, we ran about 10,000 jobs per day was our peak. And a lot of these jobs are actually deploying OpenStack using Devstack and running full integration tests against running OpenStack Cloud. So they're not just simple PEP8 checks, they're real integration tests. And we're doing them up to 10,000 times a day. So the only way to really manage all of this, 10,000 tests a day, a bunch of services and tools, is to automate everything. And so we do. And here we see the Zuul status page. Zuul is our gating and automation tool. And it runs our tests for us. It schedules them in Jenkins based on Gerrit events. And what you're seeing here is that it's running a bunch of tests in check, which is where code goes when you first push it. Gate, which is where we do our project gating. Post is post-merge, so we can do things like publish documentation there or collect coverage. We've also got queues that can do code releases, so you can release directly to PyPy using a git tag, and that goes through the release process. So Zuul is kind of automating much of this process. We also use Puppet and a little bit of Salt to manage more of the infrastructure layer services and tools. But the idea is that if we can't automate it, then we probably don't do it. Otherwise, it would just be far too much work to do. And it's not automated on a cron job. Most of the automation is driven by human interaction and events that come out of the code review system. And that looks like a little bit like this process flow. So you clone master of some project locally, say Nova. You check out a branch to fix the bug that was bothering you. Hack on it, fix the bug, commit it, and push it to Gerrit. At that point, Zuul sees that, hey, there's this new code. We need to test it. It hands it off to Jenkins. Jenkins does full testing for it and reports that back to Gerrit as a +1 if you pass or a -1 if you fail. And it links back to its build logs and gives you as much information as it can about what happened there. And the idea is that if we can provide that information as early in the process as possible, the code reviewers and the submitter can see up front, does this code work? Does it pass PEP 8? And so on. Eventually, you go through this process. You might have to iterate several times. And once the code reviewers are happy and Jenkins is happy, you'll get approved. And since we don't merge code until it passes tests, that's kind of our way of, as humans, saying, please merge this code. At that point, Jenkins tests it again. And it's testing it in the way that it would merge. And if you pass, then you get merged into master. And then the process starts again, right? So if you clone from master at that point, the bug fix is in, and you can hack on the next one. But all of that automated testing is happening based on events rather than just on a cron or hourly, daily, and so on, which is more common for traditional CI environments, right? You're pulling off of trunk, testing it. We're doing it kind of upfront based on user-generated events. And the same is true for the Puppet and Salt that we use to manage the infrastructure itself. When code changes to Puppet manifests or Salt, what does Salt call them? I forget. Pillars? Those are then applied to the environment and automatically pushed in. And so that, again, it's driven by human interaction rather than just cron job type CI. And since this is driven by human interaction, Gerrit, our code review system, is a big part of that, because that's kind of what most people interact with. It was developed by Google for Android, and it uses a standalone patch review system. So it's not like GitHub pull requests. Instead, it's a lot more like the Linux kernel git mail patch workflow, where you're pushing patches around. But in this case, it's centralized. So rather than emailing someone a patch file, you push your Git commit to Gerrit, and Gerrit generates a change for you, which is then reviewed. One of the big things it does for us, though, is it's got a lot of integration points. There's hooks that you can run, a lot like Git hooks, so post-receive, when a change merges, and so on. We can take events and do things with those. You can also do JSON queries against the change lists, so you can see the current state of changes in review. And a big one is it has an event stream. So rather than needing to rely on the Gerrit hooks internally, we can feed off of an event stream and deal with things in a hook-based fashion external to Gerrit itself. This is nice because you can kind of detach your actions from a privileged environment where the hooks would run normally. Let's see here. Newer versions of Gerrit, which we haven't been able to upgrade to, also have a REST API, and they have a plugin interface too, so you can extend the core of Gerrit. We haven't quite managed to upgrade to it yet, but that's the goal, is that we'll get there and be able to take advantage of those things as well. They also allow you to configure and extend the review categories, so things that people are allowed to vote in. Verified is where your CI system would vote. So CI system says this code passes tests, I verified it +1, or you fail, verified -1. Humans interact with the code review category, which is where you say, I reviewed this code, this looks good to me, +1, or this looks bad, because you need to fix these things, -1. We also have an approved category, which is what we use to indicate that this code is approved and should be tested for merging. So this is what a change looks like. Is that big enough? Hard to tell from here. But the basic idea is that you're given a change owner, the project that it was proposed against, the branch that it was proposed against, an optional topic. The commit message is kind of the header. So the idea is that up front, you know what this is about. Then you've got all of your review information in a table-based format, so you can quickly glance and see, what is the state of this thing? Does it need more review? Does it need to be addressed by the submitter? And so on. Gerrit has a concept of dependencies, so if you've got multiple commits in Git that you push to Gerrit at once, Gerrit will sort out the dependencies between those. So a parent of one commit will need to be merged before the child can be merged, and so on. And then there's patch sets, right down there at the bottom. You iterate on these. So your initial push to Gerrit creates a change. Code reviewers say, please fix X, Y, and Z. You push another commit, and that becomes the second patch set. And you iterate on that until everyone's happy and the code gets approved and merged, which is the state that this particular change is in. A big thing that Gerrit does that I think a lot of code review systems take for granted, and I think is side-by-side diffs. I don't know. People always like that Gerrit does this for them. It's not perfect, though. It won't do all files on one page. Like a GitHub pull request, you can kind of have everything together, which is nice. But having side-by-side diffs is very handy to reviewers. We've also integrated it with our bug tracker, which we use Launchpad for, and we're using those Gerrit hooks to do this. So when you push code to Gerrit, a hook fires. We then check the commit message for special bug strings, and if one is found, we can then update the bug in Launchpad itself. And then when you merge that code and that change, we update that bug to indicate that the fix was committed to the repository. And this is one of those things that I take for granted, but whenever it breaks, everyone is very happy to let us know, and we try to fix it right away. It's a popular feature, but often overlooked. But it's not always easy to interact with Gerrit. In particular, pushing code to Gerrit can be a little clunky. You have to know, to do it by hand, you have to know a little bit about how Git refs work and how to push a local Git ref to a particular upstream Git ref. So we've built a tool that we call Git Review, which is an external Git command that you just install, in this case with pip or using your package manager, that we use to interact with Gerrit, and it solves a lot of these pushing code problems. It's easy to integrate into your existing Git workflow, so rather than doing a git add, git commit, git push, you do a git add, git commit, git review. And that will push your code to the specified branch in Gerrit. There's zero configuration, at least on the user side. So we configure git review in each project. So it's, from a user perspective, there's zero configuration. Each project should be pre-configured for you. And it can be used by any project. Wikimedia is using it with their Gerrit. There's nothing OpenStack specific about it, other than your Gerrit needs to accept pushes over SSH. Gerrit itself, if you try to push code to them, they only accept pushes over HTTPS, so Git Review doesn't work with them today. And that's what it looks like. So testing. So now we've got a code review system. We need to test the changes that are going into it. We have two major categories of tests, and we're overloading unit tests here. Sorry. But basically, we consider a unit test to be anything easy to run. Move the mouse out of the way. Easy to run without root on a local machine. So anyone should be able to run it regardless of their privilege on that system. We've also got integration tests, and these are harder to run because they typically require root. You need to be able to stand up an actual OpenStack cloud and run tests against the thing as a whole, and that requires running services as a privileged user, installing packages often, and so on. So it's a little bit harder to run for a developer. There's some issues running tests, particularly when you want to do project gating. A big one is you want to test the effect of merging a change. You don't want to test the change itself as is, because the idea is that it's eventually going to get merged, and we want to protect the end result. We don't want to break master. And so we end up testing the effect of merging things rather than the actual content of the change itself. So, for example, if master is moved ahead of you, we will merge you onto master before testing you. For integration tests, we use single-use slaves where we spin them up, run tests on them, and throw them away. And we do that because we need to give root to the test environment. So we can't trust that machine once tests have run, because again, it's coming from users on the internet. They can push arbitrary code. We need to protect ourselves from them doing bad things to the machine, so we discard them. And we use cloud billers to do that. So today we use Rackspace and HP Cloud to spin up these machines. And one of the things we found is you can't always rely on Nova Boot working 100% of the time. So we've had to detach that process from the testing itself. And then there's large numbers of similar projects. We need to, in many cases, run PEP8 on like 20 different projects. We want to be able to store that configuration in a template-like system. There's no sense in managing each of those individually in Jenkins. So we've had to come up with a tool to solve that. And I'm going to talk more about how we've attacked each of these specific things. And then a big one, which we kind of side-skirt around, and this is one of the last things I'll talk about, is disparate hardware configurations. So, for example, something like Neutron, it wants to interact with lots of different types of network gear. or Cinder can talk to different storage backends. We don't want to host a data center with all of these different things that we have to become experts in ourselves. And so we've found a way to work around that. But the idea is that we want to test these things, but we need a way to offload the management of the test environment to someone else. So for testing the effects of a merge, we have a little shell script that we call Gerrit Git Prep. And essentially what it does is it runs at the start of your Jenkins job, and it constructs the Git repository in the workspace to test what we intend on testing and not the actual change itself. And what that means is it cleans the Git repository, so there's no leftover junk from the last test run. And then it pulls in the change that we want to test and merges it against the branch that it's proposed against. And then the idea is if that passes testing, we have a good correlation to the fact that it should pass when we actually try to merge it, rather than testing the change as it exists in Gerrit itself. For integration testing, we have the issue of needing single-use slaves. So we've built a wrapper for Devstack called Devstack-Gate that manages the single-use slaves for us. It boots fresh servers. It then runs Devstack on them to spin up a cloud. And then it runs the integration tests against this mini little cloud on a single node. But it also manages the Git repositories for that cloud project. So for example, you've got a change against Nova. We need to make sure that that Nova change is merged against master or whatever branch it was proposed to. And then we also need to manage Swift, Cinder, Glance, and so on to make sure that we're testing against their current master branch, to make sure that the projects kind of move in lockstep and that one can't break another. So Devstack-Gate has a function in it that's like Gerrit Git Prep on steroids. It does it for all of the projects rather than a single project. There are problems with this. Integration tests are slow, at least compared to like lightweight unit tests that a developer can run locally, because you end up needing to spin up an entire cloud. You're interacting with it. It's a nested cloud because we're hosting it on a VM in another cloud. So that's slow. And Cloud API calls can fail. So single-use nodes, we want to spin up new ones each time. That fails occasionally. And a fun one is external services are unreliable. So like PyP or apt repositories and so on, when you're hitting them 10,000 times a day, they're going to fail a significant, like greater than 1% of the time, you will have a failure from external sources. And so we've had to work around those as well. So to deal with this, we cache as much of the data as we can. So Devstack-Gate spins up a new node. It then prefetches all of the packages and repositories that it needs so that they exist on this machine, and then we snapshot it. And then all of our test slaves are booted off of this snapshot. So anytime a test slave starts, it's got all of this data pre-cached, and we don't have to go hit external sources. And we do this once a day, so you're only ever about 24 hours off of some external source. And so it tends to be pretty reliable. And then we maintain a pool of these nodes. So rather than spinning up a new machine every time we need to run a test, we have some pool of some size, and I think it's about 30 right now. So at any given time, we have 30 machines ready to go. Jenkins can go grab it, run a test on it, and throw it away. And then that way, we can deal with failures in cloud APIs at a pool level rather than a test level. So we failed to spin up a new node for the pool, well, we just do another one, and no tests failed as a result. And for slow tests, we've recently started running them in parallel. So Tempest can now run all of its testing in parallel by partitioning the test set and then running them in different processes. And this was important because Tempest runs were taking about an hour almost to run through a full integration test suite against an OpenStack cloud. And running in parallel, we've got that down to about 25 to 30 minutes. And that was going from one process to 4. So it's not a linear speed up, but it's helped quite a bit. So we have tests, we have a code review system, we need some way to tie them together. And we've done that with Zuul, which is our gatekeeper. It sits between Gerrit and Jenkins. It feeds off of the Gerrit event stream, so it knows what's happening within the review system, and it triggers jobs in Jenkins via Gearman. And we've done this because it allows for very flexible automation. We can use it for testing things and publishing documentation, publishing packages to PyP and so on. But the real killer feature is it allows parallel testing of serialized changes. So in a gated project, the naive implementation is you have one commit that gets approved, you test it. If it passes, you merge it. If it fails, you don't merge it. And if while that test is running, someone else approves another change, you wait for the first one to finish testing before you do anything with the second one so that your Git repos are always consistent. So in a naive implementation, if your integration tests take an hour, you can only do 24 builds in a day, right? Because you're serially queuing them up and doing them one at a time. And that's a major bottleneck. So what Zuul does is it decided that that's not acceptable. We need to go quicker. So it serializes the changes across all of the projects. It assumes that all of their tests are going to pass and that we can merge their code, and then runs the tests in parallel. And the idea is run as many tests as we can, assume they're going to pass. If they do, we merge everything in the same order that we tested them in. And if they don't, well, we can deal with failures when they happen. And the typical failure handling is if a project in the middle of this queue fails, you stop running any of the tests for changes behind it, because they might fail due to the failing change in front of them, right? So cascading failure type thing. But there may not be anything wrong with the things behind them. So we need to restart then after we've canceled all of their jobs without the failing change in the middle. There's a fun simulation for this. I spent far too much time hacking on JavaScript to make this work. But here we've got a Nova and Keystone head. Let's say it's a master branch. That's the current state of things. And your code reviewers propose 4 changes. We've got the first and second against Nova, the third against Keystone, and the last against Nova. Because Zuul is going to assume they're all going to pass, it starts their tests in parallel and all at once. So they're all running tests in parallel. And eventually, Keystone change number 3 fails. So we need to handle that. And again, what we want to do is we want to cancel the jobs for 4 because it probably failed because 3 is just not working. And then reparent 4 against 2 to remove the broken change from the queue. And then restart its job so that we can see if it will pass without the broken thing ahead of it. And we call that using the non-nearest failing item, which has a fun acronym of NNFI. But we'll see what that looks like. So we cancel the jobs. We move 3 out of the way. Reparent 4 to 2, and then retest number 4 without 3 in the queue. Eventually, that one passes. So change 3 was at fault here. And we can start merging things. And we merge them in the same order that they were proposed for merging. So in this case, 1 is going to merge first. 2 merges second. 3 is discarded. We actually report back to Gerrit saying, hey, we were unable to merge this for whatever reason. Test failed, or code couldn't merge, there was a conflict, and so on. And then test 4 passed as well, so it can merge against Nova. And we end up with that Git tree. All automated. Yeah. It's really neat. It does end up thrashing your test system quite a bit if you have failures that happen. But the idea is that, if humans are reviewing the code, they can kind of pre-filter and say, okay, this is good, it shouldn't fail. So the incidence of failure should be very low. So we can deal with failure when it happens rather than trying to, deal with it up front. And the configuration for it is actually really simple and generic as well. So we call it a gate queue. You could call it anything. So you could set your name to, I don't know, this is Ghostbusters. And so the gate is just a term we use for it, and it's in the configuration. So anyone can use this for however they want to configure it. And Zuul comes with 2 pipeline managers. A dependent pipeline manager, which is what we use for gating. And what a dependent pipeline manager does is it constructs those changes in that serialized way and runs tests in parallel. So it understands that there's a dependency between these things that are interrelated. You set up triggers for them, saying, this is when you start a test. In this case, if Gerrit has an event where a comment was added with a value of approved 1, start the jobs that are configured for this pipeline. We can then take action when jobs start, when they succeed, and when they fail. In this case, on start, we reset the verified vote in the Gerrit change. On success, we set the verified vote to +2, and then we do a submit true. In Gerrit land, it's not called merging, it's called submitting. You do a submit to merge code. And so what Zuul is doing is it's telling Gerrit, this code passes tests, please merge it. And on failure, we set a verified -2, so that way the code cannot merge until we retest it and come back with a +2. And then you apply that to individual projects. So in this case, Nova has a check pipeline, a gate pipeline, a post, and a release. So using the gate pipeline from the previous example, anytime that trigger matches, we're going to run these 4 tests. We're going to run a PEP8 test, a Python 2.6 test, a Python 2.7 test, and a Gate Tempest Devstack VM, which is the integration test. And then how Zuul sorts out how dependencies, where are the dependencies between projects, is anytime you have a job that has the same name between projects, that implicitly creates a dependency between them. So in Keystone, Swift, Glance, and so on, they'll also have a Gate Tempest Devstack VM job, and that builds a relationship and a dependency between them. So it's very generic configuration. You should be able to, anyone else could be using this as well. There's nothing specific to OpenStack here. And in fact, Wikimedia is using it, and I want to say is AT&T as well. Yeah. Another big problem you have when you want to run 10,000 jobs is that configuring jobs in Jenkins is not fun, especially if you do it by hand or with the XML. So what we've done is we've built a tool called Jenkins Job Builder, which allows us to template our jobs and write them in YAML, which is a lot more readable than XML. And then that way we can write a job, say, for PEP8 once, and then apply that to Nova, Keystone, Cinder, Glance, and so on, without needing to manually curate these things. And so we manage all of these YAML files in Git. They're code reviewed just like everything else in Gerrit. And then Jenkins Job Builder compiles them for us and pushes them into Jenkins via the Jenkins API. Another nice thing that it supports is the grouping of jobs. So we can collect a bunch of jobs that are, say, related to Python projects, and then apply this group to all of our Python projects. And it really trims down the configuration. This is what a job template looks like. It's super simple. Like, setting up something like this in Jenkins by hand is not very simple, but here it's, 10 lines of YAML. Variables can be interpolated. So here we've got a name and GitHub org variable. Those are interpolated by their values passed in when you apply the template. And this basically says there's a job with this name. When you build it, do Gerrit Git Prep first, and then run PEP8 with these arguments. And publish the console log to our log archive. To apply a template to a job, or to a project, you create a project section with a name, a GitHub org, because those were the 2 values we needed in the template. And then under a jobs list, you list the template. And Jenkins Job Builder will then interpolate those values into the template, and you get a job for free, basically. You write it once, and now 20 projects can use it. And there's also examples of our job groups here. We've got Python jobs and translation jobs as well. And that's collections of a bunch of jobs, and we don't have to then iterate through each one and keep those in line across many projects. Instead, we can group them and do it in one place. Another side effect of running lots and lots of jobs is you generate a lot of logs. For the current cycle, it's just over 2.3 terabytes of compressed logs. And so for a long time, it was very hard to determine, trends and across failures and things like that. Say this exception, how often does it occur? Or has anyone else seen this particular failure in this test? You could get reports back for your particular test and see why it failed, but you couldn't really get any more information than that. So we've been working on using Logstash and Elasticsearch to normalize and filter the logs and then index them. And then that way, test fails, you can go find an exception, the failure itself, and look it up and say, is this consistent? Am I the first person to run into this? Has someone else solved it? And what's really exciting, and this has just happened recently, is we're using it to drive automatic failure classification. So we can write queries for Elasticsearch that indicate a bug was, this bug causes this thing to happen in the logs. We can then, on a failure of a job, check in Elasticsearch for occurrences of that particular query, things that match that query. And then we can say back in Gerrit, hey, I think you ran into this particular bug. And the idea is that we can generate this feedback loop where we can determine which bugs are most problematic, at least from a CI perspective. and where should we focus energy on fixing things and so on. And that's been, Joe has been working on that, and that's been really helpful so far, and it's only been working for like a week. And scaling hardware needs. So I kind of mentioned this earlier on, that Cinder, Neutron, etc., they interact with particular pieces of hardware. And we don't want to have to learn all of these hardware devices and manage them and so on. And so what you can do is set up a third-party testing. And it's really easy. You basically subscribe to the Gerrit event stream like our test tool does. And if you see things in that event stream that you care about, say the file for your particular hardware's driver in Cinder or Neutron was modified, you can then run your test locally and report the results back to our Gerrit. And then that way you can give feedback upstream to say, please, -1, this breaks our next rev of hardware or whatever. And then that scales a lot better because the folks building the drivers and the hardware, they understand it, they can manage and maintain it themselves while still giving good feedback upstream. And third-party testing has been used by several people at this point, and it works really well. Smokestack runs tests against Zen, whereas we use QEMU and KVM upstream, so that feedback against different hypervisors. And I think the Trove guys are using it as well to do testing for things like when Devstack breaks them or when Nova breaks them. So on Nova changes and Devstack changes, they're running their test suite locally and reporting the results back upstream, so that the idea being Nova won't break Trove. And that's it. Thank you.